Hey everybody. So we're going to do a quick video on some of the remaining ideas from derivatives of vector functions. So let's jump right in. Let's start with a vector function. So remember, if I have the function r of t is equal to, right, it's going to have three component functions. And we defined the derivative, right? Or really this just fell out of the way we talked about limits of vector functions, that then we get our regular old derivatives from real valued functions from first quarter calculus stuff. We just have to do it for three different component functions every time we take a single derivative, right? And in a similar way, we can take second derivatives, right? Exactly the same thing happens. So there's not a whole lot to say about that. One of the things we said, a derivative was, one way to interpret a derivative is as it produces a vector that's going to go in the direction that we will think of the tangent line as going. So we want a tangent line to a space curve. What we look at is the vector function, its derivative, and that gives us the vector that's going to define the direction of that line. It also can be interpreted as, if this original function is a position function, it can be interpreted as velocity. It's a right. It's when you take that derivative, that difference quotient is like a difference of placement vectors. So it's the displacement vector. So it's the total displacement, or an average displacement divided by time, and that gives us a velocity vector, right? Displacement per unit time. Okay, so what I really want to do in this video, though, is add some properties. Okay, so this is not much to say about these double derivatives, second derivatives, but let me give myself a few functions to work with here. So let's say I have two vector functions, u of t, v of t. I'll have a scalar, let's call it c. So I'm just using the notation is in the set of real numbers. And then I'll have f of t is a real valued function. Okay, so notice there's no bar over it. That's just our regular old, you know, f of t equals t squared minus 1 or something like that. Just a regular old, these are going to all be differentiable, meaning that their component functions have different derivatives, or f itself has a derivative. So we want to look at some rules about what happens when we start combining derivatives. So for instance, if I take the derivative of u of t plus v of t, we get the expected this, and of course we can throw a negative on there. It doesn't change much. I'm not going to prove all of these. I'm going to do one of them at the end. They're all pretty similar if you just go through the definitions of derivatives and the definitions of vector addition and things like that. They all fall out pretty simply. If I take the derivative of a constant times a vector function, so we're scaling our vector function, we just get that constant times the derivative of that function. We can also do something like this. Here, I'm scaling a vector function by a real valued function. So for each value of t, u of t produces a vector, f of t produces a number that scales that vector, right? So sometimes you might have something like u of t is pointing in the right direction, and then you use your scaling function to make sure it goes the right distance to whatever it is you're looking at or wanting to point at. There are various reasons why this kind of stuff shows up. And so what we end up with is a version of the product rule, the derivative of f of t times u of t plus f of t times the derivative of u, right? So again, we're using some notation here, and we have to keep in mind what things are, right? The derivative of f is just our regular old derivative. The derivative of u is a vector derivative, like the one up here. This little dot that I put in here is the product of a scalar and a vector. So that's our scalar multiplication. F of t can be thought to multiply by each component of u prime, right? Same thing on this side, that this multiplication is scalar multiplication. Let's see, what else? What about this, though? If I take the product of u of t dotted with v of t, now that's the dot product. And it turns out that we get a nice version of the product rule here. Nothing strange has to happen. Derivative of one times the other one plus the one that had a derivative is now doesn't have a derivative times the derivative of the other one, right? And again, oops, I missed my dot here. These dots are dot products, right? So it looks very similar to the one up here. I guess I could put this in for completeness, but the dot, we mean different things, right? Up here, we mean scalar multiplication. Here, we mean the dot product between vector functions, right? Again, if you want to prove this, take two functions, take their dot product, take the derivative, and you can use some algebra. You'll see that you can put it into this form with some rearrangements of addition and so forth. Similarly, if we have a cross product, I'm going to stop writing the of t just to simplify this. We'll get u prime cross v plus u cross v prime. Okay, again, another product rule. Now, again, these are cross products. This one has some particular care needed. With the dot product, the order I wrote this in doesn't matter, right? This, I could have written this as v dot u prime, and this one as v prime dot u, and it wouldn't matter because the dot product commutes, but not so with the cross product. We have to be careful that whichever one's first over here remains first in both of these cross products on the right. Let's just clean that up a little bit. That looks a little ugly. All right. There's our cross product. All right, and then one more, and this is the one I'll prove in a moment. d dt. We can even take the derivative. We can do a chain rule, sorry, a composition where we put, instead of the input to u being t, we end up with u of f of t, and we get a very similar result. We'll take the derivative of u and leave the inside alone, and then we multiply by the derivative of the inside. Now, we usually just write this at the end when we're doing real valued functions. We put it up front. I mean, it doesn't really matter. There's nothing that says I have to write it this way, but we typically put our scalar multiplication in the front of our vectors. So we get f prime of t times u prime of f of t. Okay, so let's do a proof of this one, and then we'll do an example of it, because I think it's also maybe not clear exactly what I mean by that. So let's say u of t, and we'll do a light proof, is just defined to be x of t, y of t, z of t. Let's assume it's differentiable, and f of t is a differentiable real valued function. Well then, let's say it this way. Let's define a new vector function, v of t is equal to u of f of t, which just means it's equal to x of f of t, y of f of t, z of f of t, right? That's what composition means. Instead of putting the input of t, the input is f of t, so we put that in each of those places. Let's take the derivative of v prime, which of course is the derivative of this composition, but I just want to point out that this is now just its own vector function, right? And whatever f is, we can just think of this is, we're putting t in and it's doing f first, and then it's doing whatever u did, it makes a new function. And the derivative of f of t, by definition, right, what we had set up here is we take the derivative of each component function. Well, we know how to take derivatives of chain rules. These are all real valued functions. So this derivative of x of f of t becomes x prime f of t, f prime of t. That's just the chain rule. Y prime f of t, f prime of t, just our regular chain rule. Z prime f of t, f prime of t. And then we can notice that we're multiplying each of the components by the same thing here. Well, we know how scalar multiplication works. That's a scalar in there. X prime f of t, y prime f of t, z prime of f of t. And notice that is just f prime of t. What's this thing right here? That is just u prime of f of t, right? It's the derivative of each component function, except instead of t as the input, it's got f of t, right? And that's v prime of t, but of course v prime was equal to u of f of t, so that means d dt of u of f of t is equal to f prime of t times u prime f of t. Okay? So maybe that helped, maybe it didn't, but notice it just came straight from definitions, like what do we mean by taking the derivative of a vector valued function, scalar multiplication of vector value functions, so no big tricks in there. Let's do an example of this though, that might help a bit more. So let's look at the function. Let's see. Yeah, we have enough space, I think. Let's look at the function u of t. And I'm just going to do a two-dimensional function to make it easier because I want to do a visualization of this in a second, and it's going to be a lot easier in 2 dimensions. This all works for our 2-dimensional vectors except for the cross product because that doesn't exist in 2 dimensions. So I want to do our old cosine of t, sine of t, right? So we've seen this one before. This is the vector function that's pointing at points along the unit circle, right? So as we change t, it starts rotating vectors, right? Like the hands on a clock. It's one hand on the clock, pointing at the different vectors, pointing at the different points on that circle, right? So if we were to take this derivative, u prime of t, looks like a pi. Let's clean that up. Oops. U prime of t is, of course, negative sine of t cosine of t. But now let's try composing this with something. Let's compose it with a simple scaling function where we're composing it with u of 2t, right? So then our function looks like cosine of 2t, sine of 2t. Well, if I take the derivative of this, let's just think about what we do here. We take derivatives of each of these component functions. Each of them has a chain rule, so we're going to have to multiply by 2. But of course, the way scalar multiplication works with vectors and this is just 2 times u prime of 2t, right? Look at u prime, we've just got 2t in there, and then we've got the derivative of 2t out front. So this is exactly this derivative rule here, okay? Let's put a little more meaning to this. Let's get a little space here. I don't think we really need all of this. Let's put a little more meaning to what we have here. So we compose this with a function, right, that multiplied the input by 2. And notice what that did. It also had the effect of making of multiplying our derivative by 2, right? So one way we can think about this is when we multiply by 2, we are doubling how quickly we go through inputs. So for instance, so this is going to be a little let's go from 0 to pi. These are going to represent t values. Let's put a couple in here. Pi over 4. Expect this scale a little bit. Right. Oops. All right, sorry about that. All right, so here we have a little number line. Let's just divide it up into quarters. So we've got pi over 4, pi over 2, 3 pi over 4, and pi. All right, so these are two values, t values, excuse me, right? So what happens to let's think about these two functions, the composition and the other, and the original, right? When t goes from 0 to pi over 4, u of t does a quarter rotation. U of 2t, well, as we put in t equals 0, 2 times 0 is still 0, but by the time we get to pi over 4, we get 2 times pi over 4, or pi over 2, which is a half rotation, right? It's gone twice as far. By the time we get to pi over 2, in this next interval, this one does another quarter rotation, and this one's still doing a half rotation. This one's doing a quarter rotation. Oh, sorry, I'm doubling everything early. Sorry, this is an eighth of a rotation. Pardon me. This is an eighth of a rotation, and then this is a quarter rotation. In my head, I'm picturing a half a rotation. Anyways, so by pi over 4, that's an eighth of a rotation, right? Pi over 4 is right here. From 0 to pi over 4, that's an eighth of a rotation, which means when we double it, we're getting a quarter of a rotation in each of these little intervals, right? And we'll just write the last one for completeness. This is a quarter of a rotation. So by the end, this one has done a half a rotation by the time we get to pi, and this one has done 1 rotation, right? It's gone all the way around once. In other words, it's going twice as fast, and we're indicating that with our derivative. Let's take a look at a graph of this. Let's see. Let's share this other page. There we go. All right. So here is our unit circle. I didn't draw the vector function. It's harder in Desmos, but I've put dots at where a particle, so really I've made parametric equations related to the vector equations we were looking at. So you can see up on the left-hand side, we've got cosine of k, sine of k, cosine of 2k, sine of 2k. All right. And just notice that cosine of k, when our input is just k, is the black dot, cosine of 2k is the blue dot, and as I start changing the inputs, that blue dot, there we've gone, the black dot's only gone a quarter of the way around, the blue dot's gone halfway around, and by the time the black dot's gone halfway around, the blue dot has gone full rotation, and by the time we finish this up, going from 0 to 2 pi, that blue dot has gone around twice, and the black dot has only gone around once, right? In other words, it's going twice as fast, so if you, the size of the velocity vectors, remember what our two velocity vectors were. So the u prime of t was just negative sine t cosine of t, and u prime of 2t was 2 negative sine 2t cosine of 2t. So if these are velocity vectors and one's going twice as fast, this one should be twice as big. Let's compute the magnitudes of these. The magnitude of u prime of t is going to be the square root. We've got negative sine of t squared, so that's just going to be sine squared t plus cosine squared t is going to be equal to 1, right? We get the, well, I'll just write it out, square root of 1 or 1. And then the magnitude of u prime of 2t, sorry, this is a bad way to write this. Let me Let me change this a little bit. It's hiding the chain rule that's happening. I should just write it this way. The magnitude of this vector, let's say it that way, the derivative of u prime of ddt of u of 2t, well, I would take the square root of each component, but notice these components, if I multiply in, are each going to have a 2 in front of them. So we'll end up with 4 sine squared of 2t plus 4 cosine squared of 2t, which is just equal to the square root of 4 or 2, right? And so this velocity vector is twice as big as the velocity vector of the old one, right? And so that's just a little bit of intuition of how this chain rule works and why we get this scaling factor on our composition of functions. Okay, that's it for this video. All right, I will see you next time. Thanks, everybody.